Thanks a lot. Good morning, all. Thanks to the organizers for accepting my talk proposal. And yeah, this is very special for me because it's the first in-person conference and presentation that I make after the pandemic. So it's kind of a big change for the past 3 years. So when I was planning this presentation, I was thinking, yeah, optical transceivers. We're working on this for some time, but it's not probably the most sexy, right, topic. And I thought, how can I make an attractive title for the session? So I was not feeling very inspired. So I ended up asking ChatGPT, what could be an attractive title, and this is what it came up with. So I will not be talking about ChatGPT, but that's a good topic for another session, maybe. So yeah, I mean, we've been working with some of our customers around how we could help them in get better insights around how their installed base on optical transceivers is behaving. And I don't know if this is something you guys are also exploring, but in this session, I want to give you some of our learnings, some of the opportunities we see, the insights that we also see, and maybe some recommendations if you guys want to tackle this challenge as well. So just to set a bit of the context in terms of what has been going on with optical transceivers maybe over the past few years, right? Optical transceivers represent a quite sizable piece of the overall capex expenditure on a network. Depending on where we look at, somewhere between 10–15% on that range. And it has been such that there's been a clear transformation in the industry from basically using the transceivers that the networking vendor was providing with the devices, and that was the operation mode a few years back. But that has changed because you guys started to realize, hey, these things are expensive, right? I would like to have cheaper options. I would like to use third-party transceivers, right? So that probably has squeezed a bit the percentage, but it's still a quite sizable percentage, right? But that has opened, of course, now a new world of opportunity for some players, right? The third-party optical transceiver providers, which are growing their business at a relevant rate. But somehow, what was probably a capex issue now has evolved into an OpEx issue, right? So probably, I don't know, 10 years back, you guys were not maybe trying to figure out, okay, what transceivers models do we have or vendors? There were no vendors. It was just, Cisco transceivers with Cisco boxes, Juniper transceivers with Juniper boxes and whatnot, nothing else to discuss. But now it's become something that you need to manage probably, right? There are multiple vendors, of course, multiple models, multiple technologies, multiple part numbers, and what all combinations are going to work and how that impacts into your network performance, reliability, et cetera. And these parts that are in thousands or tens of thousands or hundreds of thousands in your networks, they also fail, and they fail at different rates, from, I don't know, 0.5 to 10%, depends on, of course, the technology and the vendor, but ultimately quality matters, and this is going to impact how your network is performing overall, right? What is the rate of failures, right? But frequently, when a part of this fails, I mean, the issue is not really, the cost of the faulty part, right? Some of these items, their cost very, very less, but what is the OpEx of going or sending someone to replace that part, right? So can we do something to improve that? Can we do something to proactively manage or to be more proactive at detecting possible failures? And maybe leveraging some other track roles to go and replace some components that are about to fail, or that maybe we have some good insights that they might fail soon. Right? So this is just a little bit of the overall context. I would like to ask you guys, maybe quickly raise your hand, those that have the feeling that now transceivers are something that you need to do more in terms of visibility and management? Can you guys raise your hands? Okay, I would say there's a quite sizable part of the team, which I think matches well with what we've seen in some of our customers. So what is the problem statement that we are trying to address somehow, and that we think now data and algorithms, right, along with, of course, now the wider availability of cloud resources can help us solve, right? First is all about the early identification of transceiver failures. Can we predict that a transceiver is going to fail, or that it's about to fail, or when it will fail? And as a consequence, enable a more proactive maintenance operation, right? That's one of the first goal that we have. And the second, now that we have visibility on all these different transceivers and types and vendors, et cetera, can we also provide a more up-to-date and accurate picture of your installed base of transceivers? That's another issue. Now, in the past, you probably were not managing that, but now you have to. You have decoupled the networking vendor from the transceiver vendor, and now you have tens of thousands of little devices, little part numbers from different vendors. Are they all behaving equally? Probably yes, or probably no. But that's a complexity that somehow you need to manage and track over time. So what are the opportunities that we have? Well, fortunately, we have for many years already the digital optical monitoring, right? That gives us a framework, at least some basic framework for some data associated to those transceivers that can be collected, and then we could do something about it. What is the data that is available in DOM? Well, there are a few interesting metrics that we can, leverage. First, temperature. That will give us a sense of, the operating range, temperature-wise of the component. It's extracted from within the component itself with a sensor. Then, of course, the transmitted and received optical power, right? Which is fundamental for the ability for the element to transmit properly or to receive properly. We will see some of this through the presentation. Laser bias current, right? The optical transceivers, they are not switched off or switched on when we need light or when we need to transmit data. They're always on in some level of power, and so that they can keep the laser in this linear range, where if you increase the power, then it will transmit a 1 or it will transmit a 0. So power always changes, right, around that midpoint that is represented by the laser bias current, which is the current that you need to keep the optical transceiver in that state, right? That's another very interesting metric that we can collect and we can analyze to determine what is the operating health, let's say, of the transceiver. And of course, that bias current exists because there is some voltage coming into the transceiver. We can also collect that. So these are 5 key metrics that the digital optical monitoring framework provides us. How to get that data? Well, it depends on the vendor. I mean, I'm just giving you here some examples, but every vendor has its own MIPS, but ultimately the meaning and the data is all there, and it can be extracted by your favorite SNP collection tool, or eventually through streaming telemetry once they are enabled in the different vendors, right? So this is the basis. This is the basic data that we need, at least from a telemetry. From a metrics point of view, we'll see what is the other part of the data that is relevant for this type of analysis. But ultimately, what we want to understand is where a transceiver is in its life, right? Because the transceiver life starts when you deploy it, and then it ends at some point. And it ends when it is not able to accomplish its mission, which is to transmit effectively the data to the other end of the fiber. And this is a very simplified picture of what happens in a transceiver over time. But essentially, the main driving factor is that the laser efficiency will degrade over time, and not necessarily in a curve like this, but it's definitely degrading progressively. It's becoming more and more resistant. So that means in order for the output power, the TX power, to be constant, because you need to transmit a certain amount of power to the other end, you need the current to increase. So you can see how the laser bias current will progressively be increasing, right, to compensate for the loss of efficiency of the laser. But at some point, the current will not be able to grow more, right? And is it at that point that effectively the output power will start degrading? And will start degrading, right, progressively over a period of time. But what that means is on the other end of the fiber, on the other end of the connection, where we have the RX power, the RX power will start decreasing. And at some point, the RX power will be below the sensibility of the receiving end of the connection. And at that point, the transceiver will cease operating as we need, right? Because it will not be effectively sending the data that we need on the other end with the power that we need. And for all practical purposes, it will be dead for that connection. It could maybe be used in some other connection, but in that one, will be dead. Of course, there will be different variables that will impact this process. And as I said, this is a simplification. I'm not including here how the other factors might change, or even the temperature conditions, etc. But this means just every transceiver life, or every transceiver is a dynamic system that is going to be evolving over time. So now we need to have, we have the opportunity with data and algorithms to get better visibility on how a transceiver is behaving, right? I've mentioned the DOM metrics, right? Temperature, voltage, power levels, etc. That's one part of the question. That gives us the real-time, let's say, information about how that transceiver is operating. But data without context, it's almost meaningless most of the times. The context that is required for the data is the metadata that we need to collect for all the different transceivers that we're getting information from. What type of metadata we need? Well, we need to know, where is this transceiver installed? What interface? What is the vendor of this transceiver? What is the vendor of the device? Right? What is the part number, maybe, or what is the type of optical transceiver? All this is information that will help us contextualize the metrics that we're getting. So one key message, and this is, of course, applicable to this use case, but also to any other, maybe, data project that you might be trying to tackle, right? Metadata is as important as the data itself, right? Metadata is the data of the data. So when we started working on transceivers, we really found it was fundamental to collect for every transceiver that information so that we could do proper analysis. And that one, it's a little bit more complicated to collect, right? Vendors are not necessarily exposing this in a standard, in an equally consumable way. So sometimes it might be through SNMP, sometimes you need to go and collect it through CLI commands, etc. But overall, the data is there. It's just that it becomes a little bit more complex to collect. But once you get the telemetry, the metrics, and the metadata, there's a lot of opportunities, a lot of different use cases that can be addressed. First of all, evaluate the metrics that you're receiving against the vendor-recommended thresholds. Those thresholds come as metrics as well, as part of the DOM monitoring. So for every metric, the vendor usually will will program on the SFP, on the pluggable, on the transceiver. What are the boundaries, the expected acceptable boundaries or operational boundaries, the high threshold and the low threshold, that the transceiver should be operating on. So you can collect that as well to compare if you are within those recommended thresholds. But you can also detect if maybe certain transceiver is behaving as an outlier, if it is not behaving as the others. We'll see this in more detail. We can track your inventory potentially of the transceivers now that you have all this metadata about vendor, transceiver vendor, transceiver type, part numbers, etc. Right? And see how that is evolving over time, and maybe even use it as you negotiate with your transceiver vendors, which I'm sure you do, right? Prices and whatnot. Maybe you can use some of that information for your own benefit. So what is the approach when you have all this data? Typically in any data project, I don't want to call it data science, but in any data project like this where, as I was saying, our primary goal is to be able to identify early, to predict, if you will, failures. So given historical data, right, about which transceiver failed and when, we could try to train a model, right, in machine learning like terminology, to predict if a transceiver is likely to fail and when, right, leveraging those input metrics. That's usually what falls into this category of supervised type of learning, right? You have data about what transceivers fail, and when. With that data, you can maybe try to predict what is going to happen for other transceivers. Then the other approach is, okay, given real-time data that I have, let's assume that I don't have that historical data, but given real-time data, you can try to identify which transceiver is deviating from, let's say, what the vendor recommends. That's one interesting angle. But also which transceiver is deviating from the other transceivers. Is there any transceiver that is not behaving as most of them are, of the same type, let's say? Or can we identify when a transceiver, by using algorithms, when a transceiver is going to deviate from what the vendor recommends, right? And use this anomaly status or abnormality as a proxy to determine if a certain part, a certain transceiver is likely to fail. This is more the unsupervised approach because you don't have that historical data of when certain transceivers fail and why. We are not using the supervised approach at this point. There's nothing bad about it, but it's that the fact that usually we don't have the data. If you guys have historical data about transceivers that fail and when, and you had the opportunity to capture the conditions that led to that transceiver to fail, that is extremely valuable. But usually, at least in the cases that we've been working on, we didn't have the data, so we could not take that approach. And therefore, we are focusing on analyzing the data that is coming in real time from the transceivers and trying to extract knowledge from it, extract information. And that's sort of the unsupervised approach in this case. In this project, like in any other that you might be working on around data and applying some type of insights, no matter how great your algorithm of choice or your model or whatever it is, the garbage in, garbage out principle applies always, right? And there's a lot of garbage in this type of data, and I'll give you some examples of that. So that means if you don't deal with that garbage, what you will get at the output is garbage as well. So I mentioned all these 5 metrics that DOM is offering, depending on the transceiver, model, or vendor, etc. Some might not be there. That just happens, right? So sometimes maybe it is an interoperability issue between that transceiver model and the networking vendor that is not able to extract it, or maybe the transceiver vendor did not program that. It could be for a lot of different reasons, but sometimes those metrics are not all available. Or sometimes they are available, but they just show as 0 all the time, which means it's garbage. It's not useful information at all, right? We've seen also, right, all these metrics from the transceivers, they have a lot of noise, a lot of spurious values. They don't represent a real value, but suddenly there is a peak, or it goes to 0 and then back to normal. So all this is going to pollute, your results if that is not handled, adequately. But that's again, a little bit of source of garbage as well. I was mentioning that the thresholds that the vendors recommend, high and low thresholds, are usually available. Only usually. Sometimes they are not, or sometimes only one is coming and the other one is not coming. So that means, more garbage, because if you are relying on those thresholds to do some analysis and the threshold is, again, 0 or not present, that makes things complicated. So more analysis that you need to do to kind of detect that type of situations. And ultimately, the challenge is that there are eventually, and the larger the network is, the more of these, many different combinations, like, device vendor, transceiver vendor, what software releases are running on the network device, which might or might not be compatible either with the transceiver or with the ability to extract the data from the transceiver. So all this leads into more noise and more variability. So there's a lot of, in this case, a lot of data cleaning and preparation, let's say, that is required for this type of analysis to work, right? So if you guys want to work into this, just take that into account. A lot of variability on the data. What type of questions are we trying to answer, or we think might be interesting to answer around optical transceivers that might lead to this possibility to predict a failure, right? So let's assume we have a transceiver at t equals now, right, in this timeline view. And we are collecting a few metrics from this transceiver, right? Power, temperature, bias current, voltage. And there are others we are not addressing yet, per lane metrics, et cetera, but they could be added, right? First question is this transceiver within the vendor recommended boundaries? That's a very simple question to answer if we have the boundaries coming as a metric as well, which usually they are, but they might not be. So, but that's a first question to address. Is the transceiver behaving as it was in the past, or has there been any change compared to what it was showing previously? Sometimes, of course, there are spurious changes, which, again, it's better to try to eliminate or filter them. But sometimes there are persistent changes. Like if there's been a change on the optical topology, on the optical network, chances are that on the receiving end, you're going to see a significant change in the RX power, right? Maybe it goes up or maybe it goes down. But that's something you might want to know at the packet level if that happened at the optical level or at your provider level, for example, right? So that's a question interesting to know if there's been any significant change in any of these metric and a persistent change. Again, not an spurious value, which usually it's just noise on the measurement. The next question, right, is this transceiver behaving differently from its peers? And who are its peers? For example, transceivers from the same transceiver vendor and the same type, right? You would expect that they should behave similarly in terms of the operating ranges for all these different metrics, or for some of them. So, so that's a valid question. If a transceiver is substantially deviating from the ones or from the likes, maybe it's because there is some kind of faulty condition developing, right? Then one of the things that might be interesting as well, as I mentioned, this data tends to be quite, in normal conditions, quite stable, like the power or the temperature or the bias current. It doesn't change very frequently, but if it did change very frequently, that might be a symptom of a hardware issue. So algorithms can help us identify if there is a variability on the metric that is way higher than it should, right? So we can potentially calculate some variability score that tells us that this transceiver is behaving differently. But also, is the transceiver data reliable? Garbage in, garbage out, right? Do we have garbage in and we need to maybe prune this data or this transceiver from the analysis? So that's also useful, because if it's not reliable, everything else that we compute is probably going to be garbage anyway. And last but not least, can we project some of these insights to the future, right? Can we get answers about when this transceiver will fail, or how is this transceiver expected to behave in the future, maybe using time-based prediction or some other algorithm, right? So these are some of the questions that this type of analysis could help answering. As I mentioned earlier, we're not using the supervised approach where, if we had a good data set of when a transceiver failed, we could train a model. We're trying to learn from the data, and that part of learning means inferring normality from the data. Like, taking advantage of the principle of, birds of a feather flock together. Transceivers of the same type, and by type, I'm again simplifying here, saying vendor and maybe transceiver type, you could expect that they should behave similarly. And if so, then we can maybe identify if any of them it's behaving differently, and maybe label that as a candidate for potential further analysis, or maybe for candidate for failure. What type of algorithms do we use to extract? There's a lot of different algorithms for outlier detection. I mean, from basic statistical ones to more sophisticated. What algorithm to use, or you can use, again, it's a choice. But it's important to contextualize the data for the proper type of analysis, by identifying which are the transceivers that are supposed to behave similarly. Because if you don't do that, if you don't compare apples with apples, then you will end up mixing data from different contexts that should not be comparable, and that will make your analysis more difficult. So what I'm showing here, it's just a statistical distribution of 4 of these metrics, the temperature, the bias current, and power, etc., for a particular type of transceiver, right? For finisar and SFP 10 gig LR. You can see the shape of this curves looks like a Gaussian, like a normal distribution. And that's the usual symptom of a very homogeneous population and the way they might behave. Of course, there is always some variability, some operating range. But what happens if you mix things that probably shouldn't be mixed together, right? If you say, okay, I'm going to analyze for finisher vendor all transceiver types for this metric, bias current, so that you start getting more complicated distributions, right? Which, depending on the algorithm that you use to detect outliers, it might or might not work, right? Or maybe you might need more complicated algorithms to be able to extract anomalies and outliers if you don't take that into account. Similarly, we say, hey, okay, let's just compare across 10 gig LR, which you could think they're going to be similar anyway, across vendors, right? And the curve is also very different compared to just looking at one vendor. Ultimately, every vendor might have its own maybe manufacturing or technology decisions on the transceiver itself, and how it is and what is the right operating ranges for the different metrics. So this results into different distributions. So what you are seeing there on the bottom right, probably it's a mix of multiple distributions together. What this all means is, it's better to leverage the metadata to contextualize. The more we contextualize the data, the simpler the algorithms we could use to extract knowledge from them. If we don't do this, then identifying who the outlier is in this distribution is much more complex. So you need to get more complex algorithms to do that. This is one key lesson, and again, applies to this project, but applies to any other analysis that you do. Correlation doesn't imply causality. You might identify correlations in data, but that doesn't mean that one causes the other, right? In this analysis, we have some input data, all these different metrics that we are collecting on a per transceiver basis. And let's assume that we somehow transform these metrics into a kind of aggregated or abstracted view of the health of the transceiver, right? Is this transceiver healthy or unhealthy? Let's call it transceiver health. What type of transformation is that? It could be a lot of different ways to do it. Just, I'm not making it specific because there's no single way to define that. Depending on how we look at the analysis, many options could be acceptable. But ultimately, transceiver health itself doesn't mean anything unless we can connect it with what you're really interested in your network, right? What you want to know is, okay, what is the percentage of transceiver failure or the error rate on interfaces running these transceivers? Or the error rate being higher than a certain value, or the interface flap rate, etc. These are the things that have impact in your service, right? Not the TX power or the temperature or the bias current. Now the key is, how do we connect in a causal way this input data into what matters to you, which is the metrics that represent the service, service degradation in your network. And for that, you need a causal model, right? Because correlation itself will not give you that. And a causal model, at the end of the day, it's a graph representation of your knowledge in the domain on how you think, based on your expertise, that certain variables might connect with each other in a causal way. And then statistics will help you identify if that causal model, with the data that you have, it's providing you the results that you expected. So let's represent some of these input variables in the graph. This transceiver health abstraction, right? These variables are contributing. There is a causal relationship. You know it because you are creating that transceiver health. Obviously, there is a causal relationship between this and your transceiver health. But now your hypothesis is, okay, how is transceiver health connected to, for example, your interface flap rate? Because that matters to you. If an interface is flapping too frequently, maybe it is because the transceiver is in a bad condition and you might want to replace it. But how can you make that connection? There could be other confounders, other variables in your environment that are also impacting, right? Both the flap rate as well as the input metrics. That's something that might require further analysis. It's always use case specific, but that's part of the analysis of building a causal model, right? Is there any variables that are impacting both my sources or my response variables that might be misleading my analysis or my hypothesis, that maybe temperature or bias current are impacting my flap rate, and maybe that's not the cause. The cause is another confounder. So that's part of the analysis that is required. And then we have statistics, right? The Bayes theorem and others that will help us ultimately connect or input, in this case, the transceiver health abstracted metric that we have created with the flap rate, because that's our goal. And again, that's our hypothesis. Can we find a connection between the data that we are collecting from the transceivers to the flap rate, for example, or the error rate on interfaces? Because if we find that connection, then we can predict whether a certain interface has a certain probability of flapping in the next week or in the next month, given the metric that we are collecting right now. So some of the work that we've been doing is helping us. I mean, what this graph is showing here is that we have seen how for a certain formulation of this transceiver health, when the health degradation is really high, we're seeing a spike in the probability of flaps on interfaces, which means we are finding that connection that helps us sort of predict, right, with a certain level of certainty that, given the metric that we are collecting from a transceiver, there is a certain probability that this transceiver will flap. When that becomes very high, maybe you might want to take some proactive, actions to manage, maybe to replace those transceivers potentially. Some numbers, right, around this type of analysis. We are talking about data, and we are talking about, thousands or hundreds of thousands of entities for which we are collecting data. So for every interface, and I'm not going to go into this, the description of each of the items, but effectively you're going to be collecting around 50 metrics, 50 different types of metrics, either collecting or building. So this is data now that you need to track, over time, maybe every 5 minutes, every 10 minutes, depends on how frequently you do it. And if we extrapolate this to a network-wide example with maybe 1,000 devices and so on, this could be easily 2.5 million time series, right, on a network. You might think, oh, this is a lot, but hey, we need to think differently moving forward, right? We're entering into a new world from a network operation perspective that is more data enabled, or data first, or maybe data centric. And the force comes at our rescue here. The cloud, the more affordability of course, storage and compute power and algorithms, right? So brute force is your friend on anything, data these days, and there's a lot of opportunities if we take advantage of the algorithms and the data to obtain insights like the ones I'm describing. Ultimately, what are the outcomes of this? Well, as I mentioned earlier, be able to proactively manage your transceiver infrastructure and not react to failures. And by proactively managing, you might be able to minimize truck rolls, be able to proactively replace those parts that are likely to fail, and in that process, minimize the amount of failures that your network will experience, minimize the churn and the service impact that might have associated. And of course, as a collateral effect, now that you have that data, you can maybe identify pockets of quality degradation and help even manage your relationships with your vendors, right? There's a lot of opportunities around data and we find around transceivers. So this is very much what I wanted to share, what we've been working on around transceivers, and there's still work in progress. We find there's a lot of opportunities to drive new insights around this, and we'll be happy to hear your feedback now or later. Any question? Do we have time for questions?
Hello, Jordan Villarreal, Netbox Labs. So when I'm dealing with optics at scale, and I have one that goes bad, and I RMA it, that gets linked back sometimes to a bad batch. And now I've got to replace 500 transceivers because they came out of that same batch. Mm-hmm. But I don't know that they're going to fail. I'm just trusting the vendor. So are you seeing any correlations in there within those batches? Like, yes, these are more likely to fail, or should I just keep trusting the vendor when they say, send me back those 500?
Yeah. I mean, we haven't seen anything specifically, but now, at least for the cases that we are working, because we are collecting both the transceiver vendor and the part number, et cetera, we might be able to identify those if we see, an aggregated, degradation or different behavior compared to others. So that, I think now it is possible. I cannot say that we have seen any particular instance of that, but that's a good opportunity.
Not like attaching like a PO number, like these data, these metrics called or anything like that.
Sorry?
You're not attaching like a PO or an order number to identify like what they came from.
Or maybe a serial number?
That could be possible if we could connect to the source of when this was purchased and connect to the business side. That's definitely possible. We are not doing that, but that's a good option as well.
Thank you.
Hi, I'm Dan. So when you're looking at these metrics, are you looking at like time or temperature kind of independent from power, or are you looking at it where if the temperature was running high for 6 months, we expect that the power is going to, like, are you correlating those types of cross metric data?
We are not doing that at the moment, but that's definitely an opportunity now that you have all these different metrics, right? It is possible to, let's say, learn how they are cross-correlated, how one is impacting others, potentially. We are trying more to focus on how these are impacting the outcome, like the flap rate or the error rate, but of course, they might be interrelated as well. For example, the case of temperature, the temperature in the transceiver is also going to be influenced by the overall temperature of that room or that device, because it might be operating in a hotter place or whatnot. So if we have also that data from the device, we can also correlate with that information. I mean, there's a lot of opportunities.
Sweet, thanks.
Hi, I have a question, Lawrence, coming from enterprise environment. How do you take this data and maybe teach the customers how to correlate it, how to analyze it? Because some of us come from an enterprise with multinational, many locations, and in reality, there is no centralized purchasing, right? Every guy, every local manager may order his equipment from who knows where, right? So there is no standardization in real life. Is what you're doing applicable in an enterprise environment?
Yeah, definitely. I think, it is, and it is the higher the scale, right? And that applies to both a large enterprise environment or maybe a service provider. I think what this brings is a unified view of that installed base that even if you are, let's say, fragmented from your procurement decision perspective, the fact that you might now have a single unified inventory of this and how that installed base is evolving, it could trigger a broader coordination among those different stakeholders to make unified decisions.
Second question, have you looked into from operational perspective, what are the benefits and drawbacks of being proactive versus waiting for the respective transmitter to go down, right? If I'm going and I'm taking outage to replace 50 transmitters, right? Because I think there's a high failure rate, which the high failure rate is nothing that I can put my finger on, right? It could be 2 transceivers over a period of 3 years, right? Because the data is the data, right? It's how you analyze it is true or false. So what have you seen? Have you seen anything from practical perspective replacing versus waiting for failure?
Yeah, we don't have quantified results on that yet. And that's the reason why we are trying to connect in the most reliable way the different insights and metrics that we collect from the transceivers to what really matters, like the probability of a failure or probability of a flap or the probability of errors. Because then we will have the possibility to say, hey, because of these metrics, we have prevented this number of, we can prevent this number of flaps, or we can prevent this number of interfaces with errors that somehow might impact. Now, the aggregated view in terms of what if we didn't do anything and we just let this thing as it is now, whenever the one fails, we go and replace it. That's an analysis that needs to be done over time because we don't have that view yet.
Thanks. Hi, Daryl Budick. I was curious about batch sizes of different optics. You might have thousands of 10 gig optics and a handful of 400 gig optics. Do you find that there's useful aggregations across vendors to compensate for small batch sizes, or do you just have to adjust your expectations by the size of your sample set for a different product?
Yeah, I mean, some of these algorithms that I was mentioning, for example, about detecting outliers, inferring normality from the data. If you have a large sample, right, that will probably give you a good reliable. But if you have, let's say, only 10 of some type, well, the quality of that analysis might not be as good. So part of the usage of different algorithms needs to take into account what is the statistical significance, let's say, of your sample. And in some cases, the output of that for that batch might not be sufficiently significant.